When a source of sound, like a ringing electric bell, vibrates, sound waves are produced. These vibrations travel in all directions through the air around the source. If the waves on their way do not encounter obstacles like a wall or some other object, they continue to travel in the medium without interruption.
This means the sound waves propagate through the air indefinitely till the energy carried by them becomes zero because of damping. Such waves are called progressive waves. They do not return to the source at all. A wave originating in a source and traveling forward in a medium is called progressive wave.
When a stone is dropped into a pond of water, waves travel from the point of disturbance till they reach the shore. Such water waves are examples of progressive waves.
Progressive waves are of two types: transverse waves and longitudinal waves. In a transverse wave, the displacement of particles of a medium is in a different direction than that of the direction of propagation of the wave. So, in a transverse progressive wave, displacement of particles of a medium is at right angles to the direction of the propagation of the wave.
For example, waves traveling along the length of a rope tied at one end and vibrated at the other end are transverse progressive waves.
On the other hand, when the displacement of particles of the medium is parallel to the direction of propagation of the wave is said to be longitudinal progressive wave.
For example, when a spring mass system oscillates, a longitudinal progressive wave travels along its length in the form of compressions and rarefactions.
The vibrations of the particles in a progressive wave are of the same amplitude and frequency, but the phase of the vibration changes from different points along the wave.
Any two successive particles vibrating with the same phase are separated by a distance equal to the wavelength lambda. The vibrations of the particles of medium give rise to crests and troughs or compressions and rarefactions. These travel forward along the wave and transfer energy in the direction of the propagation of the wave. The energy carried by the wave is the sum of potential energy and kinetic energy of the vibrating particles at every point.
Here, the vibrating particles of the medium transfer energy, but they do not move forward along the progressive wave.
Look at this ringing bell. The sound wave produced by it travels forward. What happens if the sound wave meets an obstacle like a wall? If the energy of the sound wave is not completely absorbed by the wall, the wave returns back. The wave is then said to be a reflective wave. This reflected wave travels in the opposite direction of incident wave.
What is the difference between the incident wave and the reflective wave?
Consider a wave pulse traveling along a stretch rope tied to a rigid wall. When the pulse arrives at the wall, it exerts an upward force on the wall. By Newton's third law, the wall exerts an equal but opposite force on the rope. This reaction of the wall generates a pulse at the wall which travels back along the rope in a direction opposite to that of the incident pulse. The reflected pulse returns with its transverse displacement reversed. Hence, a wave reflected from a rigid end undergoes a phase change equal to pi or 180 degrees.
On reflection from a rigid or fixed end, a wave undergoes a phase change of pi or 180 degrees. We will now do a simple experiment.
This string is attached to an electrically vibrating tuning fork. The other end of this string passes over this pulley and is tied to a pan with some weights. The weights provide the necessary tension in the string. Then the string is called a stretch string. When a tuning fork is excited, a continuous wave travels along the stretched string. When this wave meets the fixed end, that is the pulley, it is reflected back with a phase change of pi. As the tuning fork continues to vibrate, continuous reflections take place at the fixed end. This means that two waves, one incident and the other reflected, travels through the string simultaneously. The two waves then superpose on each other. This superposition gives rise to a resultant wave called stationary or standing wave. A stationary wave is formed when two waves of equal frequency and amplitude travel in opposite directions along the same path. A stationary wave actually traps energy between two fixed ends. Since the energy remains stationary in the medium between two fixed ends, the resultant wave is called a stationary or standing wave. The energy remains stationary between the pulley and the tuning fork. The single string appears as double because of formation of loops or segments. The appearance of loops is due to simultaneous travelling of incident and reflected waves. It is seen as such because of the persistence of vision of our eye. The appearance of loops is a result of the energy oscillating between two kinds, that is, kinetic energy and potential energy. Although the reflected and incident waves travel in opposite directions, they are actually in phase because the incident wave is reflected twice, that is, once at the fixed end and once more at the tuning fork end. Therefore, the wave travels a distance of 2L. Loop formation takes place only when 2L is exactly equal to n lambda, where n is equal to 1, 2, 3 or 4 and lambda is the wavelength of the wave produced by the tuning fork. When 2L is equal to n lambda, the string will be in resonance with the tuning fork. In a standing wave, there are particles which undergo minimum displacement. These points are called node and are shown by n. Similarly, there are particles which undergo maximum displacement and the points are called antinodes as shown by an. Two successive antinodes are separated by distance equal to lambda divided by 2. Distance between a node and a successive antinode is equal to lambda divided by 4. The wavelength lambda is twice the distance between successive nodes or successive antinodes. In a standing wave, the crests and troughs or compressions and rarefactions do not travel through the medium. The vibrations of particles of medium in a loop will be having different amplitudes. The vibrations of all particles within a loop are in phase. The wavelength and frequency of a stationary wave are the same as that of the incident wave.
Let us now compare the properties of progressive wave and stationary wave.
Let us look at the difference between progressive waves and stationary waves. Progressive waves are produced by a vibrating source and continuously travel forward in the medium. Stationary waves are formed when two waves of equal frequency and equal amplitude travel in opposite directions along the same path. Progressive waves travel in the form of crests and troughs or compressions and rarefactions through the medium in all directions, whereas stationary waves are confined to a fixed region of the medium where they form nodes and antinodes. Another difference to look at: in progressive waves, all the particles have same amplitude and frequency everywhere in the medium. Every particle undergoes the maximum displacement at one time or the other. Whereas the stationary waves have amplitudes of different particles in the medium are different at different points. It varies from a minimum at nodes to a maximum at antinodes. One more difference we can look at is, in progressive waves, the phase of vibration changes for different points along the wave. At any particular instant, different particles have different phases. In stationary waves, the vibration of all points within a loop are in phase and are out of phase with respect to the points in the adjacent loop. Another difference we can look at: in progressive waves, distance between successive crests, that is compressions, or troughs, that is rarefactions, is lambda. In stationary waves, the distance between successive nodes or antinodes is lambda divided by 2. Another difference between progressive waves and stationary waves is, in progressive waves, energy is carried continuously by forward moving waves throughout the medium, whereas in stationary waves, energy is trapped in a fixed region of medium. One last difference I can think of between progressive waves and stationary waves is, every particle in progressive wave undergoes maximum displacement at one time or another, whereas the particles at nodes undergo only minimum displacement in stationary waves, while at antinodes they undergo only maximum displacement.